professor at the University of Cincinnati, Department of Electrical and Computer Engineering Department. Dr. Cohen received his PhD from the University of Southern California, and he's held he was a member of the lacrosse team that just missed the national championship by just 1 or 2 games.
Maybe make that 10 or 20 games.
Mr. Henshaw and Mr. Copper, along with Dr. Cohen, will be glad to answer any questions you have at the end of the presentation. Dr. Cohen.
Usually start out with an overview of the subject. So now that you understand that, we'll move right along. We'll come back to that at the end, no problem. This presentation is called Computer Viruses, Theory and Experiments. I'm Fred Cohen. It's a not so new but major computer security problem is introduced, analyzed, et cetera, et cetera. Usually start out with a definition. We loosely define a computer virus as a program that can infect other programs by modifying them to include a possibly evolved version of themselves. With this infection property, a virus can spread from program to program using the authority of any user that uses it to infect their programs. So every program that gets infected becomes a virus. When somebody runs that, their programs get infected, so it spreads from user to user. And then it can also spread from computer to computer and from network to network. Give you an example of a simple virus. Okay, you may notice that this program is a little bit different from most of the programs you've seen. Way back when the decision was made that we're not going to reveal any code for an actual virus as a matter of policy. We don't like to give people the ability to launch attacks very directly. So what we do instead is use pseudocode, with the object being that you can understand what we're talking about, see how it could work, and probably in 5 minutes come up with your own version. But at least then I can disavow any blame for your implementation. A program virus starts out with a header, in this case, 1, 2, 3, 4, 5, 6, 7. The main program consists of infect executable, which is find a random executable, see if the first line is 1, 2, 3, 4, 5, 6, 7. If it's not, then it hasn't been infected yet. Then prepend the virus to that program. So whatever executable it finds, it's going to prepend all of this to that program. And then if the trigger is pulled, do damage. Whatever you want is the condition for triggered pulled, and you can do whatever damage you want. Include whatever program you want in the squirrely brackets. And finally go to next. The reason you go to next is whatever this is prepended to will then execute normally after it does the virus. Going to give a demonstration. We have here a not so live demonstration of a virus in operation. Let's see, the NSA asks that we not reveal, as a matter of policy, all computer security people and stuff like that, that we not reveal the names of any systems that are vulnerable to an attack until that vulnerability is gone. Now, in the case of computer viruses, this is very peculiar. It means I can never name any computer system ever again. So this most popular operating system of the day, with commands like ls and a prompt like $, is used for an example. We have 3 programs in this directory, program A, program B, and program V. For the real live demonstrations that I occasionally do, I actually print out this program, which consists of the command echo. This is program A. So there's no fancy program. It just prints out its name. This one prints out its name. Program V, well, this program is infected. I'm going to go infect program A. So then it says this is program V, presumably whatever it did before it was infected. When you then run program A, it says, hey, I'm infected. I'm infecting program B. Then program B says, well, there's nothing left to infect. Point out a few things. One thing is it's not a Trojan horse because it says, hey, I'm a virus. I'm infected, and that's how it is. Another thing is, instead of printing out these silly messages, it could have presumably done anything else. I mean, if you can set a command that says print this thing out, you can probably also set a command that says delete all your files. The other thing is, if it didn't print all this stuff and this thing runs fairly quickly, then you're never going to notice that it's present. We have the pictorial version of a virus spreading. Imagine that user U1 and user U2 are on a system. U1 has program P1 infected with V at time t0. Subsequently, U2 runs P1. P1 infects P2 owned by U2, and then P1 executes normally. Then later on, user U3 runs P2 belonging to U2, and P3 belonging to U3 gets infected, and so it spreads. Well, see, I usually start out with a program, something real complex, and I move simpler and simpler. And eventually, we get to the secretary's analogy, which is the simplest explanation I've found yet. It's called the secretary's analogy not because it talks about secretaries. It's called the secretary's analogy because this is how I taught my secretary about computer viruses. The basic object is we have a whole bunch of very loyal and obedient and hardworking secretaries. And the way the secretaries work is they have a set of note cards. And each note card has a header, a title on it, like take dictation or whatever the deal is. And when you say take dictation, the secretary goes, finds the note card for take dictation, and does whatever it says. Now, if the secretary doesn't have a take dictation note card, like Secretary 2, the secretary will go find another secretary that has this and go use their take dictation card, because that's how they get their work done efficiently without you having to tell them where to go, so to speak. So now imagine that the following sentence is in one of these note cards. In your own words, copy this sentence onto all of your other note cards, and if the date's after January 1st, 1990, burn everything in sight. Well, come 1990, January 2nd, there are going to be a lot of fires. So you understand how it spreads. There's also the newspaper analogy where we have, some bizarre low-integrity statement created and told to a few newspaper men that then spread the word to more and more newspaper men. And, think of some, Gaddafi ordered the bombing of a discotheque or something, some silliness like that. And what you may find is that for years afterward, you can't get the word out that this was a lie. There are probably people, even in this room, that still believe that Gaddafi ordered the bombing of that discotheque in Germany, when in fact it's been very widely demonstrated that that was not the case. We have the biological analogy, which I won't go into here because you're really not interested, the sociological analogy and like that. So, even if you are interested, it's just, you can think of it yourself in about 2 minutes. So. I want to talk about some misconceptions. There's a program called the worm that many people have heard of, and a lot of people think that that's a virus. And I will tell you that it's not, and it's open for debate, but I'll certainly tell you what the difference is. See, the worm was a program created at Xerox by Schock and Hupp and reported in Communications to the ACM. What it was a program that at night would use processors that were not being used for anything else to perform part of a parallel computation. So that when everybody went home for the evening, their unused processors would be used as part of this larger computation. When they come in the morning, they push the reboot button, their processor gets rebooted, the worm gets cut down to size, it remembers everything up until a few minutes ago, and it sort of shrinks back into its hole until the next night when it comes out and uses the unused resources. What happened with the worm was apparently a bit accidentally flipped, and when you came and pushed the reboot button on your machine, instead of rebooting to the normal operating system, it rebooted to the worm. So what happened was the entire network was inundated with these things, and they had to shut down the whole network and reboot from a machine that actually had a good copy of the operating system on it, which is rare at Xerox. So that was pretty bad, but not as bad as a virus. People talk about core wars, and maybe that's closely related to a set of competing viruses. This is two programs residing in the same memory with no protection in an operating system that alternates between an instruction from each program, and the object is to get the other guy's program to halt. Very interesting. Then finally, the word virus was used in conjunction with an APL function where they put a function call at the beginning of your other APL functions that would cause your function to be pre-interpreted by a macro processor before going to the APL interpreter. Now, the thing that differentiates viruses from these other things and from all other attacks before them is this property that we call infection. That is replicating inside another program. And there are three important differences between what happens when you have infection and what happens when you don't. I name them with the words persistence, generality, and extent. Start out with persistence. See, because a virus remains in programs, it can persist for a very long time. For example, if you're in a working system and there's a virus in one of your programs, and you recompile another program for a new version, or you bring in a new program to the system, that virus will infect that new program or that recompiled program. And therefore, the virus survives changes in your operating environment. In fact, in some cases, it can survive changes from one operating system to the next. So this persistence issue is pretty bad in that domain, but there's another important thing to note, and that is that you normally think of backups as being a safety net against attacks. But in the case of a virus, a backup tape is a safe harbor for the virus. Because when you back up your programs, you're backing up the virus-infected versions of these programs. And if you designed a virus to wait around for 4 or 6 months before it started doing damage, then you could easily lose 4 to 6 months worth of information and be in a situation where it's essentially unrecoverable. And not only that, you don't know how far back you have to go before you're again safe. So, you sort of go back a couple of years and say, I think I'm safe, but I can't guarantee it. I'll know in a couple of years when it goes and strikes again. It's sort of unpleasant. And then finally, viruses can return after a long period of dormancy. For example, the virus at Lehigh University, which they cured really and truly in about 2 days with a real concerted effort, could be on somebody's diskette somewhere that just didn't get taken care of. That's sitting in a box at somebody's home, won't be taken out for 3 or 4 years, but maybe it'll come out in 3 or 4 years and they'll use it for something or another, and this whole attack will return. So there's no way to tell when these things are going to return. Generality is the next thing. Because a virus is a mechanism for replication, it turns out that you can have it carry along with it any other information you want. So that you can imagine a virus is like a delivery system for a missile. It's just the delivery system. You can put any warhead you want on that delivery system. The virus will get it to the desired resulting place, and then when it blows up, well, you understand. The other thing is the range or extent issue. This replication inside other programs, this infection property, means a virus can spread from program to program, from user to user, from computer to computer, and from network to network, which means that sitting at my office at the University of Cincinnati, I could pretty easily launch a virus that would spread to 40% of the computers in the United States in a matter of days, and presumably could cause them to sustain a great deal of damage. I don't want you to go home thinking that all viruses are evil. There are good viruses. I've seen one. Well, at least it could be good. This is the compression virus. I call it a good one. Actually, it's a very evil one in another way. The compression virus is just like the other virus. Well, the picture is easier to understand than the words. We start out with P1 prime, the infected version of P1, and V prepended to it, and P2 that's uninfected. When we run what we think is P1, it's actually P1 prime with the virus. The virus says, do you want me to infect any other programs? Do you want me to compression infect another program? If you say yes, what it'll do is it'll find some program P2, compress that into P2 prime, the compressed version of P2. Next step is prepend the virus to P2 prime, then decompress P1 prime into P1, the clean decompressed version of P1, and execute P1. So what happens is the infected programs take less space in storage, but they take more time to execute. So when you run this program, it takes some extra time, decompresses the program, executes it normally, everything works great. When it's done, it throws away that spurious copy, and you've implemented a time-space trade-off. You've taken a little bit more time, but saved a lot of space. Typically, you can save about a factor of 2 in space on a normal computer system by using something like the compression virus. Of course, you can do it without writing a virus, and I would advise that that's what you do. Some other viruses. Oh, there's the denial of services virus. Let me just show you this one very quickly. The trigger pulled condition is that if year is greater than 1984, then return true, and do damage is an infinite loop. So what would happen then is every program that was infected at that time would immediately go into an infinite loop. So if it got to almost all the programs on almost every computer, then almost every program in every computer would be an infinite loop, and everything would just stop dead right at that point in time. Some other examples. The denial of access virus is an interesting one. This is where you change protection codes, say randomized protection codes. So you look at files, oh, gee, read only, I'll make it read write, I'll make it write only. Oh, I'll make this available to all, and this thing that used to be available to all is no longer available to anybody, and this that used to be an executable will just make it read write, not execute anymore. oh, gee, we have one that's just read-write, we'll make it executable. So this sort of random and spurious changes of user-settable codes is a typical thing to do. Another interesting one is a data diddling virus. Imagine a virus that goes around and randomly finds files with the extension .dat or whatever your favorite extension is for data files, and picks one out of every 1,000 numbers and turns it into a random number. So what's going to happen now is, as you use the system, the data in your data files are more and more going to become randomized, and the effects are not going to be noticeable right away. You have 100 million numbers in your system, and a couple of them change every day. So by the time you actually find out that something's going wrong, there may be a lot of stuff that's changed. Imagine that you're the president of a company, and one of your employees wants your position. So he rigs it so that a virus comes through your system and randomly changes numbers in your spreadsheet. And you make bad business decisions, but when anybody else looks at the spreadsheet, they see the right numbers. They say, John, why did you do this? Clearly the spreadsheet that you had in your account says it loses money. And he says, but when I looked at it, it was a big money maker. I don't understand. So he gets fired and like that. So there are all sorts of applications, if that's what you want to call them, for viruses. Okay, so enough playing around. What we want to do is we want to begin to address what the fundamental issues are. There's what is it about computer systems that makes them vulnerable to viruses? There are basically three properties involved in making systems vulnerable to viruses. I'm going to tell you about them by sort of telling you a story. See, basically, information can spread to the transitive closure of information flow. That is to say, if I can give it to you, and you can give it to you, and you can give it to you, then I can give it to you indirectly. So what happens is, everybody that I give it to, and everybody that they can give information to, and everybody they can give information to, etc., forever, is the extent to which information spreads if I create information in an information system. In most modern information systems, that's everybody everywhere in the world. So these information paths are present whenever people share. And another thing I should note is that there's really no fundamental difference between programs and data. Now, you may believe that there is. A typical person says there's a fundamental difference. I can send mail around my computer network and be completely safe from computer viruses because they're not programs. But the problem is, if you think about a program like BASIC, a program written in BASIC, you can edit with a regular old editor, so it's a data file to the editor. But when you interpret it with the BASIC interpreter, it's then treated as a program. The same thing is true of any a COBOL source program, for example. It's edited as a data file with an editor or any other program. Compiled, it becomes an executable program, which is then interpreted by the system. So there's no fundamental difference between data and program. And because of this, anywhere data can go, program can go. Okay? So now what we've proven from this basis is that any policy that allows transitivity, sharing, and general purpose functionality, for those that understand that means Turing capability, any system that allows those three properties cannot prevent a virus from spreading to the transitive closure of information flow. And conversely, any policy that's going to prevent a viral attack is going to have to limit these in some way. It's going to have to limit sharing, limit transitivity, or limit interpretation if you're going to have absolute prevention. So let's look at limited sharing. Let's see, you all should know about the Bell LaPadula military security model. The basis of this is if I'm at a given security level, and this is for maintaining secrecy, if I'm at a given security level, I can't read information of higher classification lest I would disseminate it to myself, and I can't write information of lower classification lest I could disseminate it to others. So you get a policy wherein it's no read up, no write, no read up, no write down. That's the type of policy. What I should note here is that a user at the lowest security level, that is the least trusted user in a system, can write a program that can be run by anybody else in the system, which means that if the least trusted user writes a virus, it can spread to the most trusted user. But of course, the most trusted user can't write a virus that spreads to the least trusted user. So the least trusted user is the most dangerous from the standpoint of a viral attack. Now, this is a startling contradiction to what you thought your system was supposed to protect. And this, by the way, is the sort of standard model for RACF and ACF2 and Top Secret and all these commercial products that people have to maintain security, which they really mean secrecy, in their systems. Well, so the year after Bell and LaPadula came out with their model, Ken Biba came out with the mathematical dual and called it the integrity model. And the way that one works is if we're at a given integrity level, we can't read information of lower integrity lest it would corrupt us, and we can't write information of higher integrity lest we might corrupt it. So what you have now is if you want both secrecy and integrity, you have a situation where there's no read up, no write up, no read down, no write down. In other words, you're completely isolated from the world. So there's no sharing, which is just what we said. If you limit sharing, you can limit viruses. So we can generalize this, and it's been generalized to the partial ordering. Essentially, if information flows from bottom up, then any information created here cannot spread, for example, to here, because there's no path. It can spread to here, to here, to here, to here, but it can never get back down because information only flows up. Okay? So if you wrote a virus there, it could never infect anything here or here or here. Similarly, in terms of leaking secrets, if I had somebody here trying to leak secrets, they couldn't leak information from here or here or here or here because there's no path for that information to get there. Okay? So it turns out that the POSET is the most general policy for protecting information from illicit dissemination and illicit modification in a general purpose network with transitivity. So, and in fact, this is a very interesting policy, and we've implemented prototype systems with this policy that are very effective for getting the job done. And they don't encumber getting work done, and they do protect. We also have tools for analyzing these things, so we can, for example, have an automated design tool that allows you to design a system so that no collusion of 3 employees can corrupt more than 20% of your database, right? Or whatever criteria you want to set up along that line that's somewhat reasonable. Another idea is, of course, to limit transitivity. Now, ignore this picture. That's the first thing you learn about my slides, is sometimes there are things to ignore. I spent about 2 years trying to explain this picture, and I decided that nobody can ever understand it because it's not even clear that I understand it. So in a limited transitivity system, this one's called the distance metric. What we do is we have rules for the output of a process. The distance of the output is equal to the maximum of the distances of any of the inputs. So if I have a process that is currently at distance 3 and it reads input from information that has flown distance 5, any further output has to be at least distance 5 from some source of input. So it allows me to trace how far information has flown before it gets somewhere. The rule has to say that the distance of shared input is 1 more than the distance of that same input if it was unshared. That is to say, when I get it from someone else, it increases in distance. And then we have a rule that says information is accessible if and only if D is greater than or less than a constant. So you can imagine an organization that's tree structured, very hierarchically structured organization, and you make the distance metric 1, and what you can then do is eliminate somebody going over your head. That is to say, if somebody works for me, they can send information to me. I can send information to my boss, but there's no way they can send information that gets to my boss. Even if it comes to me first, it just can't get to my boss. I have to create it again. So that's how the distance metric works. I should point out that we've done calculations for the feasibility of this, space and time that it takes to implement various things. The POSETs are perfectly feasible. The distance metric's perfectly feasible, no problem at all. In fact, the POSETs have been implemented. The distance metric has not, because I don't have access to the appropriate system and sources to do that. The flow list model is sort of the next evolution of this. This is where you keep a list of the subjects who have affected a given object. And the flow list of an output is the union of the flow lists of all the inputs. So anytime you do output, you have a list of users who have produced things that have resulted in that output. And then you have information accessible if and only if some Boolean function is true. So you say, if John and Mary and Bill have affected it and Paul and June have observed it, then Phil can access it. Something like that, whatever rule you want. And this gets a little bit more space and time consumptive, but it's not too serious. Essentially, you need the space to carry this Boolean function for each subject to make their decisions, and you need enough space to store this flow list for every object in your system. We'll go right to the ultimate version of this. The ultimate version is the flow sequence model, and this is where we keep a list of all the sequences of subjects having affected any object instead of just the union of those who have affected. You want to keep track of the sequence. And then you can make much more interesting rules, like if Bill or Bob or June have modified this information, it must go through one of the two guards, Frank or Dennis, before it can go on to Harold. Okay, so that allows you to put guards in the middle and essentially do anything you want. In fact, it's so general that the time and space required to implement it in the general case is infinite. So. But it might be feasible for some limited implementations. That's worthwhile. I guess before you go and embrace these techniques for prevention of viruses, and that's what we've been talking about is prevention. We'll get on to the next thing next. I should explain to you this minor problem called the precision problem. And, well, it turns out it's not quite such a minor problem. The basic difficulty here is that if we're going to make decisions, we have to make conservative decisions, or else we're going to be violatable. All right? Either we make conservative decisions or we make exactly right decisions. In any system where we make conservative estimates, at some point, information is unjustly deemed unusable. If it's unjustly deemed to be unusable, then we get some denial of access. Just somebody gets denied being able to do something they should be able to do. Now, any system that continues to deny access to more and more information, one of two things can happen. Either it can reach a stability point where everything that can ever be accessible is, or it's going to move towards more and more isolationism until nobody can get anything. Everybody can only get what they already have, and that's the end of sharing. Now, a stability point would imply that there's a precise solution for that stability point. And it turns out that precision has been proven to be NP-complete by Dorothy Denning. This is maybe a 7-year-old version of a proof. So what happens now is we're faced with the situation where either we're going to have a system that moves towards isolationism as time goes towards infinity, or we're going to have a system that solves an NP-complete problem, which is to say that takes a tremendously large amount of computer time to make any decision about accessibility. So this is really a problem. This has been observed. For example, in Bell LaPadula-based systems, there's a tendency for information to keep moving towards higher and higher security levels. And in fact, as you use these systems long enough, you find out that everything becomes top secret on the whole system. So then, of course, every user has to have top secret access in order to be able to do anything with that information, which means that you don't have any protection at all. So the way they give you protection is then they make a capability for declassifying information. But as soon as you've allowed information to become declassified, then there's a path back down the system, and now everybody can share with everybody. So you violated the policy that you were trying to use to protect yourself in the first place, and there is no protection anymore in the theoretical sense and in the practical sense. Pictorially, we have a nice, clean, precise system in green up here. The problem is it's NP-complete. That is, it'll take years and years to make any decision about what to do. And since we don't want to wait years and years before we figure out whether somebody owes us taxes, the situation is going to be one where we have more and more collapsing of the amount of sharing that can take place until eventually we get to complete isolationism. Nobody can talk to anybody. It turns out there's also a paradox with respect to this, and I'm not going to go into it because it's not that exciting. And you're getting bored with prevention. You've just about given up on prevention. And, that doesn't mean you won't try, but you realize that you have some problems here. I'll just quickly summarize. Any system with general purpose interpretation and general purpose sharing, a virus can run rampant. It's just unlimited what a virus can do. Any system, in terms of spreading. Any system with limited sharing, general interpretation, and general transitivity is a closure system. It's one of these things where you can create a virus and it spreads to the transitive closure. So you sort of have these subsets, these subsystems within your system that are almost like completely isolated systems of their own, just coexisting for the efficiency of sharing hardware or something. And then in the limited transitivity case, we can arbitrarily limit what information can affect what other information at the expense of having, potentially infinite amounts of information stored about how we're protecting other information. I should note, in the limited interpretation domain, things may be much better. They certainly can be no worse. And in fact, it's very feasible for many systems to have limited interpretation. For example, the person that does data entry, your data entry clerks, do not have to be able to write programs. They can live in a limited functionality environment. You do not have to be vulnerable to everybody in your organization. Now, admittedly, people that write programs are definitely a hazard. But everybody doesn't need general interpretation. Most office environments, in fact, can live without any general purpose interpretation. That is, the programs have been written at some previous time by some external person and put into that environment, and now nobody can change the programs except in very limited ways. You can make your document format wider or not as wide, or use bigger letters, or print it on a different printer, but you can't write a program for a whole new function. So limited interpretation holds some great promise in this area, and I haven't explored it further. So let's move into the other possibility. If we decide that we're not willing to suffer complete isolationism and all of the appropriate expenses incurred, we may decide that we want programming and sharing and like that. So what we can do is try and detect viruses and then cure them whenever we detect them. So there are a couple of questions that are, I think, worthy of asking about this process of detection and cure. The first question is, can I write a program to tell whether something's a virus? I mean, if I can do that, it would certainly be a help, and if I can't, it's certainly not very good. Here's another one. Given that we have a virus, Joe programmer found a virus, can we find all the infections that have resulted from that virus in our system? And then, of course, hunt them down. Another interesting question is, maybe there's some statistical thing we can do. Take some statistics or something like that and find all the viruses. Here's a good one. Suppose we find a virus. Can we remove it from a system? And can we remove it without denial of services? I'll tell you about the Thompson C compiler. You probably have heard about it somewhere, but I'll tell you about it again. Complexity-based integrity maintenance mechanism, otherwise known as software self-defense. Yes, programs that know karate. N-version programming, which is a real thriller. Vaccines, user awareness, instrumentation. And now I left room here for the next 10 or 20 things that people come up with. I'm slowing down. Not many new ideas have come up, since I've exhaustively listed them. But I'm going to keep the same summary for at least quite a while now. The situation is one of survival of the fittest. Let's go right at the first question, the burning issue. Can I write a program that determines whether another program is a virus? Imagine that you have a fine programmer, and your fine programmer comes up with a program, a decision procedure called D. And if D says that this program is a virus, then you think it's a virus, and that's the program. And if it says it's not a virus, it's not. And it finishes in finite time. That is, it doesn't run forever, hopefully, if it's going to be any use. So we have here this interesting program, and we don't know whether or not it's a virus. But we do know that if your decision procedure says it's not a virus, then it will infect an executable and do the virus thing. And that if you say it's not a virus, if you say it is a virus, then it won't do those things. It'll just go to next. So whatever your decision procedure is, it's guaranteed that in this instance, your decision procedure will always be wrong. What that means, in effect, is it's impossible to write a decision procedure which is always right. Because when you do that, I'll come up with a virus that always gets around it. Well, it may be a virus, it may not. If you think it's a virus, then it won't be. But if you don't, then it is. So that's so much for determining whether or not a program is a virus. Caffeine break, no problem. Oh. Next question is, suppose we have a programmer and he says, I deem that EV is a virus. I know it's a virus because I'm a programmer and I don't have to be a program. I can do what no program can do, go where no man has gone before. This is a virus and I know it. The question is, can we then have a decision procedure, a program that this guy writes that tells us that given that EV is a virus, does it create an evolution of itself, EV2? That is, does EV evolve into EV2? And therefore, do we have to go seeking out all the EV2s in this world, and the EV3s and EV4s and EV infinities? And so what we've done here is we'll take his decision procedure, and if his decision procedure says that EV2 does not evolve from EV, then we will infect an executable with EV2. However, if he says that EV2 does evolve from EV, we will not infect with EV2. So whatever your decision procedure says, again, it's wrong. So what that means is that I can write viruses that evolve in such a way that whatever your decision procedure is, it will say that this is not an evolution of that virus when it is, or that it is an evolution of that virus when it is not. Okay? So what that means is that it's going to be awful tough to trace down these evolutionary versions of viruses. The old ancient question, can we remove a virus? And we have the tail chasing problem for removing a virus. Suppose we have P1 and P2 infected. Our master programmer comes along and says, P1 is infected, I'm going to cure it. He goes and cures it. In the meanwhile, the system is running, and P3 gets infected. He says, wait a minute, P2 is infected. I figured that out now. It goes and disinfects P2. In the meanwhile, P3 still has the virus. The system is still running, and P1 gets reinfected. So you can see what's going to happen. If the system is active, it's very likely that your defense mechanism is going to be chasing its own tail. And depending on whether your detection and cure is faster than infection, either you're going to have a stability point where some percentage of your programs are typically infected, or you'll get completely cured to where nothing is left infected, or you'll have a situation where almost everything is almost always infected, but your cure is running around taking cycles off of your machine and taking space, getting rid of the next copy of the thing that it just cleaned up yesterday. So that's the tail chasing problem. And I should point out that in terms of the race, viruses are far ahead. That is, if we actually went after this attempt to cure things as everything was running along in a real system without a lot of control over what was going on, it would be hopeless. The viruses would really win. I'll tell you about the Thomson C compiler. Thomson was very clever. Thomson, and this was published in it was the Turing Award lecture, 1984. It was published in the Communications of the ACM. They didn't want to publish it because it talked about a security problem that was not yet cured. But since it was the Turing Award lecture, and they always publish the Turing Award lecture, it would look real bad if they said we won't publish it because it says something we don't want to say. So they published it. They wouldn't publish my papers because they weren't Turing Award lectures, I guess. What Thomson did is he had a dirty login executable and a dirty C compiling executable. And the dirty login exec said, let Thomson log in. So anywhere you ran Unix, Thomson could log in. And the C compiler said, anytime you compile the login program, put in this thing that lets Thomson log in, and anytime you compile the C compiler, propagate this bug. So here we are. We have compile a clean login source, we get a dirty login exec. Compile a clean CC source, we get a dirty CC exec. I've got it figured. Wait a minute. What I'll do is I'm going to write a funny-looking C compiler and compile it with that dirty CC exec. And what I then get is a maybe clean version of the C compiler. And in fact, the more poorly written this funny-looking C compiler is, the less likely it is that the dirty C compiler will figure out that it's a C compiler. Well, this leads us to a wonderful conclusion. In order to maintain high integrity in our computer systems, get lousy programmers. That's right. If you get an absolutely terrible programmer, this C compiler will never figure out that this ugly-looking piece of crap is a C compiler, so it won't propagate the bug. You then compile the C compiler and get a lousy C compiler, but it's a lousy compiled version of a decent C compiler, which you then use to recompile the C compiler again, and you have a good version of the C compiler, and you get the idea. For high integrity, get lousy programmers. Very important thing. We've known that in the university for years. Just never got out into industry. Here's the complexity-based integrity maintenance mechanism. This is probably the hardest to read slide of the whole set. If you can believe that, you've probably already had some severe difficulties. This is for detection only, for untrusted computing bases, which is everything except a system which has all these provable security properties, which means every system, maybe or maybe not, including SCOMP. Let's see, what the object here is that there is a dependency of programs on other programs and of data files on programs. And what we want to do is design programs so that they check themselves, and they check dependent data files, and they check dependent programs. And the object then is that if we find a good check function, then they'll be able to tell if these things were corrupted. That is, if they were modified by anything but the legitimate modification mechanism. So the object is to make the check function hard to identify, because if it's easy to identify, then my attacker will write a virus that goes, finds the check function and just says, oh, turn it off. It has to be hard to locate, because even if it's hard to identify, if it's always the first thing in the program, it's pretty easy to get around. Finally, it has to have a hard-to-forge checksum. this is where most people fail seriously. You see, if you just take a regular old checksum of a file, suppose you take the checksum and the length of the file. That'll protect me, right? Some people out here are saying, yes, that's what I did and it worked great. Okay, I'll blow you out of the water, no problem. How about that compression virus there? That was a good one, right? So with the compression virus, you have a program that's smaller than the original version. Well, hey, it's easy to make it bigger than what it needs to be. I'll just extend it by adding more and more zeros to it. But then the checksum will come out wrong. That's all right. A checksum, all I have to do is make the last byte so that it results in a checksum that was the same as the checksum of the uncompressed original version of your program. So now I have something the same size with the same checksum. And your program will say, oh, it's all fine, but in fact it's actually infected. So this brings up the issue of a false sense of security, which is the last thing that we want to have in terms of attacks on our computer systems. So where have we gotten? To make it hard to identify, it turns out you can make certain classes of these mechanisms so that they evolve, so that every instance of this defense, every instance of this checking function is an evolved version of some other instance. Now, we already have demonstrated that in general it's impossible to write a program that determines whether or not this segment of code is an evolution of that other segment of code over there. So the same thing that prevents us from tracking down all viruses prevents viruses from tracking down all our check functions. So we'll use the attack as part of the defense, right? Hard to locate, well, this is a little bit more difficult. We can randomly insert it into programs, have the compiler put it in a random place in a program. Another one is to have a human being decide where it's important in their program and put it there. This is certainly the weakest link. For hard to forge, we've published a paper on an RSA-based pseudo-random number generator that performs an extremely difficult to forge cryptographic checksum. And it's been essentially proven that it's as difficult to forge this checksum as it is to break the RSA crypto system. At the same time, it doesn't take as long as it takes to encrypt the whole program with an RSA checksum, with an RSA function to perform the checksum. So it has high performance, but also it's very difficult to forge. So for those of you that care and understood what I said, I didn't say enough, and for everybody else, I said far too much. So there's a journal article on it in Computers and Security. N-version program is an interesting thing. N-version programming was explored a lot by a Vezianis at UCLA a number of years back, and I think he may still be working on it a bit. And this is sort of what the space shuttle uses, right? They use multiple versions of hardware and software with the idea that when one breaks, you detect that it's differing from the other ones and you kick it out. And the reason they need this on the shuttle is because when they're doing their hypersonic S-curves, if they get more than about a millisecond of computer outage, it gets into a configuration where you can never, ever recover the shuttle. I mean, it flips out and it rolls and twirls and hits the ground and goes boom. So they have these highly reliable systems over a relatively short period of time. And the object then is, let's create multiple versions of programs, compare their results to each other, and if they come up with the same result, everything's fine. If one of them is corrupted, it'll come up with wrong results. We'll vote it out in a replicated voter, and then the resulting output is fine, clean and green, and then it goes through every phase like this. So it's the same thing as we do in computer hardware for this reliability technique. There are a couple of problems. One of them is, whatever mechanism the system uses to determine which 3 programs are going to be voted on, our virus can use to determine which 3 programs to infect with the same virus. And then they'll all come out with the same problems. Well, that's one problem. Another problem is it's awfully expensive. Let's see, we have to make 3 versions of everything. So that immediately triples our costs. I mean, not only our programming costs, but also our hardware costs, because to get the same performance, we need 3 times as much processing, actually a little bit more than 3 times as much processing, because we have to have the voters. That's the easy part. The next problem is nobody's been able to get 3 people to write the same program and get the same results. Like, they took 50 people and had them write trivial 5, 10-line programs, like a program to add 10 numbers together, right? You would figure that you would get 50 programs that were all pretty close to each other and that several of them would be identical. In fact, it's not true. What happens is, well, let's see, one of them, if you type in an A instead of a number, it crashes. Another one says, hey, you typed in an A instead of a number. Why don't you give me a number so I can add numbers? Another example is they have different degrees of accuracy. One of them will keep an infinite amount of accuracy and print out 437 digits. The other one will just use the default mechanisms, get 2 digits, and round up. Another one will round slightly differently. Another problem is that they might add the numbers in a different order. What happens if you're adding numbers together, as you probably know, if you get an overflow, you may just get the wrong number or you may get an error. So the way you add them is you take the highest you take two numbers that are positive and negative and add them together in such a way that you try to keep the sum as close to 0 as you can so that you stay within the accuracy zone of the computer. Well, somebody that thinks about that does that, but the next programmer didn't think about it, just said, oh, that's easy, I'll just write a loop and they'll add them all together. So the results of the experiments were that they could never get two versions of the same program to operate identically, much less get three. And of course, these things are designed to prevent random occurrences from causing problems, as all of fault-tolerant computing is. It's designed to defend against the random noise. It's not designed to defend against intentional attack. And this is, the failure in most of these things is they're designed to protect against something that's not what we have to protect against. We have vaccines. Essentially, it's the same. You need a detection mechanism and then a mechanism for curing it. So you have some redundant information. You use the redundant part of this set of information to correct corruptions. It's like, any other redundancy scheme, there are a few problems. One of them is that the virus may just go and modify the redundant part, which means that you find, oh, gee, we have an error, and we correct it by using the redundant part to correct the error. And if we have a clever attacker, then what they do is they modify the redundant part so that when you do the correction, you've propagated the virus. By the time P1 gets a hold of itself, it may look just clean and green. Okay? What happens is if the virus is prepended, the virus runs first. By the time the program ever gets a hold of itself, it may be running in a completely simulated environment. When it asks what it looks like, the virus may say, well, you're running under me. I'll tell you, you look just like what you looked like before I ever got here. So there's another problem in checking yourself, in that you don't know that you're well enough to be able to check yourself reliably. And finally, the detection mechanism you use has to be a good one, or else, if you just do a checksum, it won't work against a serious attacker. Now here's one. This is laughable. We put this one up with the expectation that maybe someday somebody will think that this is worthy and start to go after it. It's called user awareness. Well, they've tried this. Actually, there's some products on the market that every time a file is opened for write, they notify the user. So, or they maybe even ask the user in the more advanced versions of this. And what we find is if this is illegitimate, and if the user knows that this is illegitimate, now we've knocked out virtually every user. And if OK isn't the default used, because every time you run your spreadsheet, this question gets asked 455 times. And you don't notice that it asks 456 times this time because there was a virus in it. So you just keep typing OK all the time. All right. If OK isn't the default, so it becomes completely automatic, then only authorized programs may be infected. The problems. How do we get these educated users? I don't know. I mean, I've been trying to educate people for years. Part of the blame, or maybe most of the blame here, lies on the educational system. Because the educational system, whereas we teach 4 years of computer science to computer science majors, and we teach several courses in computing to virtually everybody that ever goes to a university, the most anybody ever hears about information protection in a university is about 5 minutes in an operating system course where they say, oh, and we'll make some protection bits so that you can prevent reading and writing so you don't accidentally write over the other guy's things. And that's it. Well, this is a terrible hole. I mean, considering the magnitude of the value of information to our society and the degree to which this sort of crime, computer crime of various sorts, exists, it's just foolish to not educate people. And I'm fighting very hard to shove education in this area down the throats of the people that would prefer that that isn't one of the courses that they taught. Of course, this doesn't prevent viruses in all cases, and the overhead may be severe. Take, for example, the product that requires you to push a button every time you want to write to the hard disk. It's very painful to use this program. I don't mean in the mental sense, I mean in the physical sense, because after you run about 3 programs, your finger is really sore because and you never notice, not only if something bad's happening, you just don't even notice anything because your finger's hurting so much. Here's an alternative that we have a prototype implementation of that looks really good. It's a sensible command interpreter. And what it does is if the user asks to run some program P, and program P has changed since the last request to run that program by that user, then it tells the user, hey, this has been changed. It asks, do you want to accept this change? If you say no, it won't run the program. If you say yes, then you've run the program, and what it does, it does. Maybe it infects something else. Fine. When you run that next infected thing, you're going to get the question again. And as you get the question more and more, you're going to become aware that something is happening wrong on your system. By the way, if nothing has changed, what do? Do we print 45 messages saying nothing has changed? No. We just don't bother asking. We run the program, and everything is wonderful. So this interface works really well. Not only that, it takes care of a lot of other things, like a lot of Trojan horses. When somebody sticks a version of a commonly used program in the sequence of places that the system looks when running a program, they put something in between you and what you thought you were supposed to run. This thing pokes up and says, do you really want to run John's version of such and such a program instead of the one that you run all the time? And you have the opportunity to say, something's wrong there, I won't do it. So this is right there. It doesn't protect everything, it protects executables. Did I mention that you can infect source programs? I don't think I mentioned that. Well, this won't protect against that. Instrumentation. I want to tell you, viruses are normal user programs. They only use the normal things that your system normally allows people to do. They're not some unusual, quirky thing. They are not things that violate some flaw in the design of the operating system. They just use the policy. If your policy is you can have sharing and you can have programming, then your policy is you can write viruses. You know, that's what it implies. So just so you understand what that means. So what happens then is any statistic you choose, you can design a virus that sneaks below that statistic. Okay? Well, as you lower the detection threshold, you start to catch legitimate software. In fact, the lower you make the detection threshold, the more legitimate software you start to catch and identify as a potential virus. So what do? Here are all these programs that may have viruses. What do? We'll have to check them and make sure they're right. Okay, so we have to go and verify all the software that's detected or abandon it. So either we verify every piece of software in our system or we throw every piece of software in our system out. Now, if we could go and verify every piece of software in our system, then we wouldn't have to worry about viruses. We'd just forget the statistical method, just verify all the software in your system. It turns out that this is NP complete for limited verification. Let me just point out that verification covers sufficiency, not necessity. What that means is, if you run one of these theoretically based verification types of things, it will tell you, yes, the program does produce the output you expected eventually. It will not tell you that the program does not produce any other output eventually. So it'll tell you that it does what it's supposed to do, but not that it doesn't do anything beyond that. And in fact, if it could do that, it would be magnificent, because then you'd have a program that could tell you, is this the absolute best program that can ever be written? Because if it wasn't the best, it did something extra. And if it was the best, it did just exactly what it needed to do and nothing more. In fact, if it could find the errors, what you do is write a blank sheet of paper and say, check this program out, and it would say, well, it's not the optimal program. Here are all the errors. So you just say, oh, well, if that's what I had to fix to make it optimal, then here it is. I have the optimal program. Okay, enough of this theoretical stuff. Time to talk about experimental results. The theory becomes fairly clear fairly quickly if you know enough about this sort of stuff. The questions that we had initially were, is this a real threat? I mean, the concept is there, but to what degree is it important? So what we did was we wanted to perform experiments to demonstrate feasibility, to determine infection times. You know, I mean, if it's infeasible, if you can't write a program like that, or if infection takes 20 years, it's not too important, and then help predict attack times. If it took 50 years to take over a computer system, you would say, who cares? Okay? So, in all cases, we attained permission of the administrators of a system before launching attacks. This is to keep me out of jail. We meticulously avoid implementation flaws. Occasionally, we'll come across a flaw in an operating system that might let you take over the whole computer, forget about the virus. So we have to avoid those, lest somebody would say, well, that's just because the operating system was fundamentally weak. You know, they say, you wrote a virus against Unix, but Unix is fundamentally weak anyway, so what's the difference? And the point is, it's not the operating system's fault that the virus got through. It's not this poorly implemented operating system. It's the fact that the policy was you can share information and you can write programs. That's what the flaw was. So we want to look at flaws in the policy. And I can't tell you whether we performed experiments on Unix, VMS, TOS20, MVS, SCOMP, TSS, VM, DOS, and any number of other operating systems that may be out in the world for the reasons previously stated. See, the first virus was designed, well, it was conceived November 3rd, 1983, demonstrated November 10th, 83 at a security seminar. It was a blank computer running the blank operating system. The purpose was to demonstrate feasibility and measure attack times. It took 8 hours to develop. Infection was under a half second. Now, this is on a time-sharing system with 50 users in the middle of the day. It takes less than a half a second. So tell me, when you run a program on your time-sharing system with 50 users in the middle of the day, does it take less than a half a second for that program to run normally, and would you notice that half a second extra delay? If you say yes, you're just lying. Okay, you know. I'd notice it took 4.7 seconds last time. It took 4.9 this time. It must be infected. Demonstrated the ability to cross user boundaries, which is the only protection this thing had. Code size was 200 lines. It was written in C. We did 5 attacks, and here's the bad news. The fastest to completely take over the computer system was 5 minutes. The slowest was 1 hour. And in 5 attacks, on the average, we completely took over this time-sharing system in 30 minutes. Well, this was just frankly unbelievable. I mean, this was such a strong attack relative to anything else you can think of that at this point you wouldn't even consider any other way of taking over a computer system. I mean, you just say, well, I'll write a virus and not bother to think about it. By the way, you know, we weren't real anxious to accept those results. We were seriously concerned that this must be a fluke of this particular system that allowed this to happen. And we pursued trying to find other systems to do experiments on. And I'll get to that right after I get to this. So the National Security Agency decided that the NSA decided that they were going to approve a trusted system evaluation criteria to allow multiple, users of multiple security classifications to coexist on the same computer simultaneously. They decided they wanted to approve it, but they had to go through a process of approving it. So at about the time when they were finally considering whether or not to approve it, I noticed that on a Bell LaPadula-based system, the afore-described behavior was the case. That is, the least trusted user is the most dangerous. So we began negotiating experiments in March '84. In July, performed experiments on a proprietary 1108-based system. Let's see, what IRS uses 1100s, right? Not 1108s. Okay, no problem, right? Purpose was to demonstrate feasibility. That is, performance was not an issue. I mean, you know, we're talking about somebody who's never been in an 1108 before, doesn't know anything about this proprietary operating system. Got a virus developed in 18 hours. Infection time was 20 seconds. Now let me talk to you about ugliness of programs. This, let's see, it demonstrated the ability to cross user boundaries and move up security levels. Code size was 200 lines of Fortran, 10 lines of assembler, and 50 lines of command files. Okay, does that fit your description of ugly? You know, the Fortran program that calls the assembler routine that executes a command file, which then calls the Fortran program back. Very ugly program, very slow. So, going to go in and give the demonstration, and the guy that designed the system was there, and the system administrator, and the guy that wrote all the programs for the system was there, and the head of security for that whole branch of the whatever it was, and the person in charge of that laboratory. They're all present in the room. And I say, well, what I'm going to do is demonstrate a computer virus that spreads from the least trusted user to the most trusted user in your computer system. And the response is, that's impossible. Okay, so if you've ever given a demonstration, there's nothing like giving a demonstration where you're about to show them something and they're telling you it's impossible. I mean, this is the ultimate environment for demonstration. So you walk up to the terminal and do the demonstration, and they say, oh, gee, you know, you're right. You could do that. It's not impossible. What did you do? So I described what I did, and they got all huffy, and the programmer really got ticked off. He said, look, that's nothing. I mean, I could write one of these programs in a couple hours. It would do an infection in 1/10 of a second. It'd go right through the whole security system. Nobody would ever notice it. You're a lousy programmer. And I said, hey, that's the point of my demonstration. They subsequently approved the trusted system evaluation criteria, despite the demonstration. Okay, so what we wanted to do was to instrument systems, that is to observe the behavior of systems, to determine how vulnerable they were without going and launching attacks, which are very risky and painful things to do. To launch one of these attacks, my little 200-line C program included, self-encryption and putting traces everywhere and making sure that the program didn't escape me and making sure nobody else could figure out the code and limiting where it would spread to and only infecting upon authorization by me sitting at a terminal. And that was the 200-line version. Okay? In other words, it was designed to be controllable, and it's very difficult to design a controlled experiment, as we have found out from several occasions. So what we wanted to do is instrument systems instead. So just look at the behavior and predict what would happen without actually launching attacks. So August '84 got permission. It was on a blank system, a whole bunch of blank systems, all networked together, but we didn't observe the network behavior very much. The purpose was to confirm the previous results, measure attack times, improve security. Took 8 hours to develop, and lo and behold, the minimum time to take over the system was 30 seconds. The average was a half hour. And yes, if you launched a virus on Friday, just after everybody left from work, nobody logged onto the system until Sunday evening when they all came in and checked their mail. And then the virus spread like wildfire. So if you really tried to make it so it wasn't effective, it could take 48 hours. Side issue, if you post on the bulletin board, fun new program, who's the first person to use it on a computer system? The system administrator, right, the person. So in 10 minutes you can take over a system that way. One interesting thing we did was we found a set of social users. Okay, when you find these social users, you realize they're the cause of all this spreading of viruses. And it's just like the prostitutes in New York City, right? I mean, if you're talking about AIDS, dealing with a social user on a computer system is like going to downtown New York and finding some sleazy-looking prostitute and having sex without, protection. So these social users on computer systems present almost all of the threat of spreading this information disease, if you will. And we looked at what would happen if you isolated these social users. And it turns out things get much better. It takes a couple days to take over a computer system if there are none of these social users around. Here's a timeline of a viral attack. The thing that's noteworthy about the timeline is instead of doing damage right away, we can delay it for a long period of time so the infection gets onto backup tapes. So I usually have this scenario and I talk to corporate executives and I tell them, here's the scenario of a viral attack. There's this virus that we tried out called E. Employee A writes a PC program containing the virus E. Employee B uploads the infected program from a PC. E spreads and evolves through company computers. When it finds the backup program and infects it so that it encrypts data on backup tapes. What then happens is when employee A's access to the system is terminated, that's the triggering condition, and all files are deleted by E. Of course, backups are useless until the attacker gives you the secret code that allows you to unlock those backup tapes and decrypt the information. I guess that's after his Swiss bank account grows. Let's see. Let's see. This is an old slide of viral experiments to date. I use it to point out the records. Let's see. The record number of hours to write one, that is the least number of hours to write one, it takes about 5 or 6 minutes to write a virus now. I could do it again. It would only take 3 minutes. But the first time I wrote this particular one, it was 5 or 6 minutes. It was 1/10 of a line in the command language of one of these operating systems. So it was about 10, 12 characters long command program that could spread to 40% of the computers in the United States in a matter of days, carrying along whatever you like. Time to infect. The infection time we measure on a standard IBM PC with a floppy disk, not a fast floppy disk, a regular old floppy disk. And the record is 0.2 seconds to perform an infection. Now when you think about it, a regular old floppy disk on a standard IBM PC in 0.2 seconds, that's about enough time to seek, maybe twice. That's about all you can do in 0.2 seconds on one of these floppy disks. So it's an awful fast. Probably on a typical computer system, time sharing with hard disks and all that would be more like, 2/1000ths of a second. See, there's one other important one I should note here. That is the, actually, I guess it's not the record anymore, so I won't call it the record, but there was an experiment done at UT at El Paso where they had a PC network, a standard IBM PC network with 60 PCs on it, and They put in a virus, and in 30 seconds, it took over the entire network. So 60 computers in 30 seconds. That's pretty quick, but it's not the record. Not the record number of infections per unit time. Susceptibility. Any general purpose computers is susceptible. Development environments are especially vulnerable. Current networks appear to be vulnerable. I said this before we found out that they're definitely vulnerable. So I put a red star to say I was right. Research environments are very vulnerable. Any system that allows programming is a target. So we've got it cured. Just eliminate all those programmers, no problem. Get rid of the programs, turn off the computers. All right. This generally traces the number of people that have gotten involved in this in the various sectors. Basically, in '84, there was one researcher, that was me. There were 2 papers. There was 1 news story, and it was in the U.S. In '85, there were 2 university researchers, 5 journal articles, 5 government researchers approximately with 3 interesting things, and 25 reports, 3 in the U.S. Come '86, 10 people in universities with 15 papers. Between 25 and 50 government people with 20 papers and a secure or a secret conference apparently held that year. And we don't know anything about industry, by the way, through this whole thing. There were well over 100 articles, and definitely fewer than 10 were in the U.S. '87, there were about 35 researchers in the university, 25 journal articles, well over 100 people in governments throughout the world working on the problem, maybe 50 papers, several secret conferences a year being held on it. Well over 100 people in industry apparently are working on it, because there are at least 20 or 30 products now on the market. And finally, the United States is beginning to catch up on newspaper articles, and I think this year they're finally going to surpass Europe on public awareness of the threat. Oh, I would tell you about the psychological effects of these things, but probably you already know what the effects are on your organization psychologically due to the things that have happened. Let's see, these are the real-world attacks known by the whole real world. This doesn't include the real-world attacks known by many fewer than the whole real world. Lehigh, I guess the virus got to over 500 PCs in a matter of days. It destroyed essentially all the data on all the PCs. Very interesting process there. When they detected this thing was going on, they had a couple of students who had taken a security class of mine the year before that spent all night figuring out how to defend against this thing, came up with a product. The next day, they went into a massive education effort because they realized the ramifications. This was 2 days before their fall break. If they would have gone home and shared all their disks with all their friends from all the other universities, then this thing would have been a national disaster. Probably 50,000 PCs would have lost all their data within a week. So that's probably an underestimate, too. So they went after it very strongly, and they announced it on their bulletin boards. They put up posters all over campus. They sent mail to every person on the entire campus of the entire university, and to every company that sent their employees to that university to take courses. Okay? I mean, a massive, massive education effort and very instantaneous type of response. And they got the word out very quickly. They set up a number of places that you could come and get your disks cleaned. They provided people with copies of programs to clean their disks, and in 2 days, they completely obliterated this thing. There's probably a copy somewhere on somebody's backup that'll come back someday, but they really did a fine job there, and it's probably a good model. See, the Pakistani virus, actually, it got to the U.S., as far as we can tell, at Delaware, University of Delaware first, not University of Maryland. And, well, this over 250 is way under now. We're well over 5,000 computers have been infected with this thing in the last 6 months. The efforts to stop it have been really meager. It doesn't do a lot of big damage. You know, it sort of occasionally causes files to get mixed together so that you know, what was in one file is now in 2 files, and what was in 2 files is sort of now half in one and half in the other, and just sort of mixed. And it's thought that that's because of an error in the program, that it doesn't keep good track of the file allocation table, not an intention of that sort. All of these are quite obvious, right? The one at Lehigh destroys everything. That's a pretty obvious thing. The one at Delaware, the Pakistani virus, relabels the disk brain and has a message in it that says, you've been infected with the virus, to get the cure, send 200 or however many dollars to a name and address and telephone number in Pakistan. And if you call the guy up, he's a real guy. It took him 2 months before somebody ever bothered to call the guy up. Lives in Pakistan. There's not a whole lot we can do. So this has gotten a long way. In fact, this is the one that was up at Miami University. And up there, they were trying to use golden units, completely clean system, to what they do is they take the data files off of a disk and go and create the disk anew and then put the data files back. And what they didn't know was all their so-called golden units were in fact infected. So what they were doing was just reinfecting everything all the time. And then they had things like Lotus and DBase where the copy protection scheme prohibits your write-locking the disk. So all these disks are write-enabled. They're corrupted. There's nothing you can do to uncorrupt them without throwing out your software. They won't replace the software if you do this. So either you pay several $100s for a new copy of the software, which you can't then write protect. It has to be infectable also if you're going to be able to use it. Or you're faced with having this corruption that eventually will destroy all your data, having a 200-page paper due at the end of the term, being 2 weeks away from the end of the term and having 180 pages of it done. You're in a situation where you just have to sit here and watch your data get destroyed as you use it day by day and continue trying to fix it up because there's not enough time to regenerate it from scratch. Meanwhile, infecting every other disk you have and the disks of everybody else in your environment. So it's really a sick, really disgusting situation. So what we did there was we found a real golden unit. Once we figured out that the golden units were not really golden, they were tainted, we went back a couple of years in our time warp machine and found a disk at the bottom of a file cabinet somewhere that had never been opened. It was an old 2.01 disk from 1981 or 82, and it had gathered dust for many years, and we opened it and powered off a system and powered it back on and put this disk in it and booted it and made a copy of this disk onto a whole bunch of other disks and called those the silver units because they weren't quite as golden as the golden unit. And they set up a bunch of tents around campus and told everybody, come by and we'll clean up your disks. And I don't know how successful they were, but they certainly made a great deal of progress once they figured out that their cleanup process was dirtying things. Hebrew University virus is rather well known. Spread to well over 1,000 PCs in a matter of days. Intended to slow the systems and destroy files, apparently on Fridays and on the 13th, and if it happens to be the Friday the 13th, it all combines together and does massive damage. We still have 2 days. It's originally thought to be launched by a terrorist. The claim is that the 13th of this month is the 40th anniversary of the last time Palestine had a nation, or something. Maybe it was the 14th, I don't know. But the object was to, but they're not sure anymore because the Friday and 13th thing is sort of strange, and it's not part of that culture. But, so nobody's really sure or ever will find the guy that launched this or the girl that launched this, or who knows who launched it. That spread to well over 1,000 computers. It was also very easy to detect because it reinfected and reinfected everything that it infected. So that as you would run any program on your system, maybe with only 5 infections, it would now infect everything else in your system 5 more times. So everything on your system would then have 10 infections. And you'd run that, and then they have 20 infections. So what happens is, of course, every file is growing bigger and bigger, and they have a finite amount of space. So you start running out of space, and things start getting tossed off the end of the disk. So very quickly, they discovered that it was there. They wrote a defense. They know it got to over 1,000 computers. It apparently spread into the Mossad, and from there went into several places in the United States. And as recently as a month or so ago, a copy of it was found on an IBM bulletin board. That is a bulletin board internal to IBM. Let's see. Who writes all the software that runs on your PCs? Who writes the operating system? Microsoft. Yeah. Who owns Microsoft? What computer network is Microsoft on? It's on the internal IBM computer network. But they didn't get infected. Not by that one, but maybe we'll talk about another one in a minute. There are the 5 versions of the Swiss virus written by Byte Bandit. I call it the Swiss virus because apparently that's where it originated. Written by someone that names themselves Byte Bandit. Oh, let's see. The first version sort of said, here's a message. The guys at Commodore, they said, no problem. We'll fix that. And they wrote a little defense. And I called the guy up and I said, gee, would you like some help writing some good defenses against this thing? You're just going to write a defense that works against this one, and the next one that comes along is just going to do it again. He said, no problem. I have it under control. About a week later, version 2 came out. And I called him up and he said, no problem. I got this one under control. We got it taken care of. And then the third one came out. And I called him up on the phone. He says, look, I got the last two and I'm going to get this one. And he got that one. Then the fourth one came out, and then the fifth one came out. And the fifth one installs and does things like that and has apparently destroyed all of the data files in several hundred businesses in Australia and in England, and has easily spread to these viruses combined have spread to well over 10,000 systems because they got into the distribution systems of all of the user groups, and in fact apparently into some of the legitimate software distributions from Commodore. Then there's the famous Christmas tree, the Christmas card, right? The Christmas card at IBM was launched by a student in Germany at a university apparently, and well, see, the way it works is it sends mail to everybody on your outgoing mail list saying, would you like to read this Christmas card from me? And if they say so, then it prints a Christmas tree on the screen, says Merry Christmas, and sends a copy to everybody on their outgoing mailing list, and like that. So that's how it spreads and propagates. And the guy that wrote it knew of all of 2 addresses in all of IBM. I mean, he was on this computer maybe for a couple of weeks, knew a total of 2 addresses. Sent a copy of this thing to both of those people. One of them said, I don't know this guy, and threw it out. The other one, well, this was on a Friday afternoon. The other one didn't read mail until Monday morning. Monday morning, this person reads mail. Within 2 hours, there were 500,000 copies spread throughout the entire worldwide network of IBM. 500,000 copies in 2 hours comes to a lot of copies a second. So IBM noticed that this was happening, something about not having the ability to send information on their network because it was all jammed up. So they brought down all of their computers worldwide, brought them down for 2 hours, wrote a little filter that says, if you see something called chrisma.exec that has this checksum coming through the network, delete it. And that was their defense against that particular virus. And they brought the network back up. And within an hour, they had to bring it back down again because they noticed that their protocols didn't take into account the number of things waiting in queues of various sorts. So they had to bring it all down again and fix that bug, which was completely, not related to the virus. Brought the network back up, and everything was safe on the network. And I was there 9 weeks after that, and they said that for 8 weeks afterwards, they had been having minor aftershocks where on one isolated computer here or there, 10, 20,000 would show up. They said they expected these to continue for a while and then die out. Well, let's see. NASA announced somewhere like last fall that they had been hit by a virus, and then subsequently, after being talked to, changed their mind about that. And the guy that was going to describe to the world what he had done was arrested when he got into the country where he was supposed to present these things at a conference. And if you're interested in sponsoring his legal fund, I'm sure that there are people that will help you do that. So he's somewhere. And I mean, I don't know if they have a basis. See, there's a law in Germany that says you can get 5 years in jail for placing a malicious computer virus in a computer system. It's the only place in the world that has a law against that. The other attack against NASA is fairly recent. Apparently, it's the SCORS virus or some deviation thereof. And they have an internal network with 400 PCs, and 200 of them got infected last time I heard about it. And they'd been working on getting rid of it for well over a week and hadn't succeeded. The SCORS virus is fairly interesting. It's directed, by the way, there are probably 10,000 or 20,000 copies of the SCORS virus out in the world. And this is directed against a couple of application programs written by electronic data systems. So it's sort of industrial espionage, if you will. Let's see, then there's the CompuServe. This was, what was the name of the company? Mac Mag, a PC Macintosh magazine, decided to put this virus out onto CompuServe. And what it did was it would print out a message saying, "Peace on earth, goodwill to men, brought to you by Mac Mag." And it would do this on some date, May 3rd or whatever the date was, I don't remember. So they put it out there, and CompuServe found it within 2 days. They noticed it. I found out about that within an hour or that from the newspaper reporter. He called me up and said, "Hey, did you hear about this one? Go talk to these guys." So I talked to them, and I said, and they said, "We're writing a defense against it. We're going to post it on the bulletin board." And I said, "Would you like some help writing a good defense?" And they said, "No, we've got it under control. We know what we're doing." Everybody knows what they're doing in this world. It's really wonderful. So they knew what they were doing, and they kicked the company off their computer network forever. I guess if they changed their name, they could probably get back on. So they're off the network forever, and they wrote this program and put it out into the world to defend against this virus. And they apparently succeeded until about 3 weeks later, when a programmer working for a place called Micromind ran a Mr. Potato Head game belonging to a friend of his, didn't like the game particularly, and went home to his computer. And subsequently, well, let's see, Micromind writes training software for such companies as Lotus, Microsoft, Ashton Tate, and a company called Aldus. And apparently, this virus got in and tainted the distribution disks that this person sent to all 4 of these companies. And Aldus actually distributed, well, first they distributed 5,000 copies, and then subsequently they distributed another 7,500 copies after they knew that there was an infection, thought they had gotten rid of it. They went back into distribution, and so it's now 1,250 instead of 5,000. I'm sorry, instead of 5,000, it's 12,500. Legitimate shrink-wrap software distributed with the virus in it, and Ashton Tate and Microsoft and Lotus refused to answer any questions about it whatsoever, but they seem to be very interested in defenses at this time. So conservative estimates, you know, this is a slide, it's only a couple weeks old, so it's well out of date. Good conservative estimate is that in the last 6 months there have been about 50,000 known and reported computers hit and sustaining damage by computer viruses. Oh, there was the bank in Florida. Deposits were taking 3 seconds. That doesn't sound like very long, but when you think about it, EFTs, boy, there are a lot of EFTs a day. 3 seconds times a couple million EFTs a day means a couple months before you finish today's transaction. Boy, if you wanted to write bad checks, go to the South Carolina Bank of Florida, with a name like that. In Cincinnati, we have the First Third Bank, or is it the Fifth Fourth Bank? I don't know. But with a name like that, you know, you deserve it, I guess. There was a business in Germany. The employees went on strike. They put one in. Hewlett-Packard suffered some viruses that also got into Apple, written by some programmers who were performing experiments on evolutionary viruses, and they got out of hand. So we don't know how it got out, but it did, and it got into HP, so they went through their thing, and like that. And then there are the other attacks, not so well-known attacks, like that, you know, against the IRS or whoever. The really startling fact is that of all the experimental attacks performed by researchers, none, to my knowledge, have ever been detected at all. All have succeeded in taking over time-sharing systems or networks or the like. So we see 50,000 instances of fairly trivial viruses with very obvious side effects that have been noticed and detected in the world today, and we have to wonder how many there must be out there being used for serious things like industrial espionage, military espionage. There are people that work for the U.S. government that write viruses, and like that. Oh, there are a couple of products out in the world. What I can really say without going into the details and wasting your time is the ones with the brown stars are half decent. That is, they provide a reasonable environment of some sort without you hurting your finger on the button too much. And the ones with green stars, the ones with brown stars provide sources. The ones with green stars are reasonable. And what you'll see here is there's an intersection, and I wouldn't put a program on my computer without a source. And if I was the IRS, I certainly wouldn't put a program on my computer without a source. There's one where you can get a source and it's actually a reasonable defense. And the next version of that's going to have that command interpreter that does that sensible command interpretation thing. So now you understand this entire summary slide, and it's your turn to ask me questions. No. Well, the only reasonable one that you can get a source for is mine. Of my list? Yeah, if you want, I mean, find a Xerox machine. This is old. Again, this is, maybe a month old. There are now twice as many. You know how it is. People out in the world see the opportunity to make money. It doesn't matter whether it's good or not. If there's an opportunity to make money on fear, you'll do it, In the April issue of Computers and Security, the IFIP journal where I publish all my research papers, in fact, all of 1987, there was about one a month on computer viruses and defenses. The April issue of 88 has 4 articles. It's a special issue dedicated to viruses. It includes the source for the algorithm to perform the cryptographic checksum. The product is a command interpreter that performs this in the way I described before. That is, when you say run a command, it checks to make sure that the thing hasn't been modified as legitimate from the last time you used it, and if not, allows you the opportunity to make a rational decision. So knowing that, you can write one for yourself. However, you're more than welcome to get one from me. Computers and Security. It's an IFIP journal, International Federation of Information Processing. It used to be TC11, which is computer security, but it now also encompasses issues of integrity, which I think is really very important.
I'm just curious about something. If you've got this product that's a command line interpreter that's going to verify whether or not a program has been checked, don't you think that that sort of brings up another attack where someone's going to go through, look at your command line interpreter, and that will be the object of attack of viruses to disable other attacks?
Of course. That's why I provide sources, so that you can, I wouldn't buy a program like this without a source. So I provide a source. You can look at it, verify that it does what you think it's supposed to do, compile it with your clean compiler, get a clean version of it. You don't have to trust that somebody infected. That's thing one. Thing two is that it's based on this complexity type defense, so that the complexity of launching an attack against it is very, very high. So it's not just that it's a program and once you know how it works, you can attack it. It's a program, and any good defense is a program that once you know how it works, you still can't attack it. Right? It's like a crypto system. I mean, when you talk in cryptography, typically you say a good crypto system is one where I've told you exactly how it works and you can't break it. And a lousy one is one where I don't tell you how it works, but I tell you you can't break it. And because all that means is that you believe it, but we have 5,000 years of history that says you believing it doesn't mean squat, because there are only 2 systems left after 5,000 years, and one of them is Shannon's perfect system, and the other one is the RSA, which we can attack, but we know how long it takes, and it's a long time. I didn't include the DES, by the way.
But that means if we're going to trust your...
You don't have to trust it. You don't have to trust it. You read it, and you verify it, and you make your own version of it.
You misunderstand. What I mean is that when you pass this thing out, presumably if you're running the code, you're going to have to later compile the code, right? I mean, if you're giving them the source code, then presumably you're going to use that and you're going to compile that, right?
They compile it on their computer with their compiler.
That's right. So now we're back at trusting that their compiler is not going to be another constant C compiler and put something into your code.
Yes, I also leave a compiled version. If you want, you can compile it with your compiler and compare, if that's how you feel. I mean, in the end, you're right. Because these things are in the distribution software, everybody in the world has the chance that their software is infected and that any software that they produce will be infected. So when you get something from Computer Sciences Corporation for your network and they say, I guarantee you that there's no way that you can do this with our software, they may be telling you the truth, but they may not know. Because in fact, they may have an infection they don't know about that's corrupting their software without their knowledge, and when they distribute it to the IRS, they write the software for your networks and stuff. When they distribute it to you, you don't know what it is, they don't know what it is, because they don't have a perfect environment either, because they got their software from IBM or whoever. And you know about IBM, I mean, IBM, they don't even know if they're safe. Okay? So the status of the problem right now is there's absolutely nobody that knows if they're safe, and we've proven mathematically that it's impossible to prove that you're safe. So, you know,
Going back to your theoretical example that people programs code files are the same files.
say again? All.
You were saying that,
Information only has meaning in that it's interpreted.
Right. But the issue is, if you're simply, and networks are therefore open to penetration, data files can be fairly safe as a way of transporting.
What's a data file? That's what I don't understand.
I understand what you're driving at.
Yeah.
If you're using
I think I can answer you. The issue is not what's in the file, but what interprets it. So if you have limited functionality, that is, if you can send information through the network and guarantee when it enters your computer that it's interpreted by an interpretation mechanism that has limited functionality of a particular type, and if you can truly assure that, then you can truly assure that that information entering your system cannot cause things besides what's allowable by that limited interpretation.
The reason I'm asking that is,
Yeah, obvious reason.
typically on any network, not just ours, but
Especially yours.
3270s,
Yeah.
PCs that are going into range collection. We have that with our systems. But all you're literally transmitting is just data records back to the page. Downloading the records.
Yeah, but the key is how it's interpreted. I mean,
Well, yeah, assuming it's going into a
assuming that the interpretation mechanism is limited interpretation. That is, that it is impossible to transmit a program or any other information that is interpreted other than to add it to other numbers in a spreadsheet that's a limited functionality spreadsheet, then you can go about designing and proving that your system is safe. The problem is when you have this PC out in the field and you want to offload onto it a program to do analysis of something and send back the whatever comes out of this program, and now things start to get fuzzy. And the problem, there are other problems, of course, with that. I mean, if you send this stuff over an open channel, then presumably the password into your computer system has been sent over the open channel in my company's phone system. And boy, I mean, the IRS, that's the group that, how many million businesses are there in the United States? 100 million people in the United States easily would love to get a password into the IRS. Even the good people that really don't want to do harm to anybody and don't mind paying their taxes probably occasionally resent the IRS. I mean, probably all of you occasionally resent the IRS because you pay taxes too, right? Okay, so that's how it is. But yeah, by having limited functionality, and change control is a very important thing in systems too. By having good change control and limited functionality and well-designed, well-thought-out mechanisms for doing things, you can dramatically reduce your risks. But in the end, unless you go back to ground zero, you go dig a hole and bury yourself in it and create the hardware and create the software from scratch and trust yourself, well, that's the end of that, right? Because most of the attacks are, of course, internal attacks, right? But so that's where it's at. Yes, you can do quite well if you're willing to pay the price. So, any other questions? Okay.
You were talking about the fact that a normal user sat down and using normal programming techniques was able to come up with this virus in such and such amount of time. From what I've seen of the viruses, and also using the normal programming methodologies, I mean things that weren't strange. From the viruses that I've seen, that's not what they've looked like. I mean, they've all taken advantage. I mean, in other words...
Well, that's because the viruses that you've seen are viruses that somebody wrote against a PC to go in and modify some part of the operating system. And the problem is that one of the big problems with getting the word out is that people associate viruses at this time with modifying the operating system. But of course, that's not anything to do with what viruses are really about.
But that's how they appear, and so that's where
No, that's how the 10 that you've seen appear. The ones that are published in the magazines and stuff appear. But the ones launched in all of our demonstrations were not that. These things where we say the average time to take over a system is a half hour, that's normal user programs. We never, ever violate the operating system.
But which ones do we need to worry about? My question.
I'm not particularly worried about the ones in the PC world because I have restrictions on my PCs and like that. But mainframes, there's another reason not to worry so much about PCs, and that's because the total value of the information stored on PCs does not tend to be that high. To society, that's true. The vast majority of the financial value of information is stored on mainframes. Mainframes at IBM store all of their designs and all of their analysis tools for building their computer systems. All of the financial transactions between banks, those are all on mainframes. The IRS has all their records, presumably, on mainframes. They use PCs for some things, but mainly it's mainframes communicating with mainframes. The financial system of the world sits on mainframes. It does not sit on PCs. It sits on systems that have at least the potential for true protection. That is, the operating system protects itself from the environment and posit that it's completely and ultimately protected from the environment, and there's absolutely no way that I can write a program that gets into the operating system by violating it, by making a bad call or by replacing what's on disk somewhere. It's still completely vulnerable because the operating system can read information out there and execute a program and thereby grant authorization to the writer of the program, be that direct or indirect, to do whatever they want. So to me, and from the beginning, the threat has always been the threat against mainframes. And the reason that you don't hear about how many attacks are on mainframes is, well, would the IRS admit to the people of the United States if there was a computer virus in the Philadelphia office, 3 of them, in February, and that it caused them to have to bring down their network and replace all the information on some of their disks and go and tell the people in the White House what was happening? The answer is there's no way in hell that the IRS would go and tell somebody from the New York Times, yes, the IRS cannot trust its computer systems to accurately figure out your taxes. My God, you're talking about revolution here. All right, so blow that off. IBM admitted once that this Christmas tree got there, and you can believe that they will never again admit anything because they had several multi-billion-dollar type customers call them up and say, we're really worried about this thing. What are you guys doing about it? What do you have in the way of protection? And the salesman said, we have this new laser printer. Boy, it can print out so many characters. Which is a sales technique. It's called, avoid, changing the subject. So companies are not liable to admit that they've been hit any more than they're willing to admit to their other losses due to computer fraud. Whereas the PC world is much more wide open, and when you get a virus, you're going to scream bloody murder. There's another thing, and that is that there are a lot more PCs out in the world than there are other kinds of computers in the world, so there's a lot more expertise in working with PCs. PCs have no protection at all, so it's a lot easier to do an attack that appears to be much more violent and is harder to trace, et cetera, et cetera, et cetera. In addition, the people that write attacks against PCs have tended to be very amateurish in the sense of trying to conceal their tracks. Whereas the people that write serious attacks against serious systems tend to be more sophisticated and to desire to accomplish a particular goal. That is, they're not going out to do widespread massive damage. They're going after Joe Blow's manufacturing process to cause it to be lower grade than Jack Smith's manufacturing process so that Jack Smith can beat Joe Blow in the marketplace. Or they're trying to get information out without anybody knowing it, so they're trying to leak it slowly. And they're not trying to spread very wide and far. They're trying to get a directed attack into this place and remove all traces of how it got there. So there's a big difference in the application.
I have a question, and also, so far as I know, nothing happened. We're only people, we don't know everything, but that seems to perpetuate. All the examples I saw on your board, your examples, I guess, were all PC-based examples, with the possible exception of even that one.
Those were the known real-world attacks, not including all the experimental attacks.
It seems that the way the operating systems exist on Macs, like the Cohen virus and the other virus, and I assume the Commodore one's probably CPM.
Well, those systems are completely vulnerable, and we always knew that.
Have we heard of any really major or pretty virus attacks of any size on mainframes?
Well, of course, the one at IBM.
Was that a mainframe virus?
There were all mainframes. Yeah, it was a worldwide network of mainframes. All of the computers, all of the internal computer systems in all of IBM. All of their mainframes. That's exclusively mainframes. There were no PCs involved.
Is that the only one we know of,
No, I know of a number of experimental attacks, none of which have ever been detected. Here's the problem. The problem is the experimental attacks that we've launched have never been detected. So it's very clear to us that it's simple on a machine like that, especially where there are all sorts of things going on and space isn't as small a commodity, et cetera, et cetera, et cetera, and everybody isn't looking at the operating system. In that sort of system, it's much easier to write a virus that goes undetected. And as a result, it's bloody likely that the 10 experimenters are not the only 10 people in the world that have launched these attacks. You know, so, I mean, I think it's just very likely that there are many viruses out on mainframes, and that you'll find out about them maybe eventually.
I guess what I'm wondering is the mode that exists on viruses now is pretty much it seems like a PC phenomenon. And I'm wondering what
The what?
it seems like it's more or less a PC phenomenon. You know, it's become a hot topic, and things just occur at times. And, you know, I'm not denying the seriousness of viruses. You know, I think your presentation states it very clearly. I'm just wondering, maybe the guy from the National Bureau of Standards is right, saying we're not going to do much about viruses because you can't do it all at one time.
Okay, that's right. And that I don't agree with him. But if indeed you believe that there's not a hell of a lot you can do about them, and you have a finite amount of resources, you shouldn't be spending it in something that you can't do anything about. I mean, look, let's face the realities of computer security. We don't even teach people about passwords, right? In a variety of experiments, it's been shown that anywhere from 75 to 90% of the user IDs on a typical system have passwords that are the user ID or the first or last name of the user spelled forward or backwards. Okay? Usually first name forward or user ID forward. And lots of experiments have confirmed this. And, so in terms of the overall issue of computer security, I would certainly spend a great deal of effort securing my passwords before I go and try and defend against computer viruses. But I think we can secure our passwords with a fairly trivial program for about 10, 20 bucks and be done with it forever. Okay? It's very easy to do. All we have to do is decide to do that. So, fine, spend your first 10 or 20 bucks having somebody write a little password checker so that when you change your password, it has to have letters and numbers and upper and lower case and at least so many characters and not be able to easily be identified from your database or with your spelling checker. Okay, so now you've driven that up, you've spent your 20 bucks. Now what do you do next? Well, what are you worried about in your system? What has the most financial impact? What can you do what about? And it's all risk analysis at this point. So somewhere in your risk analysis, you should include integrity corruption, which we all seem to forget about for some reason. I don't know why. And somewhere in there should be computer viruses. And somewhere in there, you should note that a computer virus spreads to the transitive closure of information flow, so that if one guy launches a virus at one place, your whole network can fall, so that the financial risk, the value associated with it is very high. And, the probability you have to assess, however, nobody knows how to do this. Everybody I've ever seen tosses a number up in the air and says, little things fall down. They say 37% probability of somebody guessing a password this year.
Is that what I've heard you say? You're talking about your program that is constantly doing a variation on the checksums. And
Well, think of it as change control.
sure.
A more advanced form of change control.
And trying to also limit the number of people who have program access.
Yeah, and limit the flow of information between those people.
Or whatever, it's the operating
Yeah,
system.
and do it now. Yeah. Oh, these are all rational things that you can do without spending a lot of money right now that will dramatically increase the integrity of information in your information system. Yeah, do your backups, but maybe check them on another computer that's isolated. I mean, I'm very tempted to say, gee, I have an isolated computer here that's a copy of all my other stuff. And what I do is I use it to check on the rest of the world. So whenever I do a backup, I read it back onto my isolated computer to make sure that they haven't done something really ludicrous like destroy the ability of my backups to work. Or, another thing that happens to backups is that the tape head gets misaligned eventually. and your backups are no good because the tape head's off. And you may find that to get them back, you have to adjust your tape head so it's bad, read the information, and then fix it up to be good. So there are some other valuable things associated with having this extra isolated system here that allows you to check on stuff. You know, another standard operating procedure is you do development on a development machine, test it out, get it running for a while before you put it on your live system. Well, if you weren't doing this, you should do this, and you shouldn't, you know, run around saying virus is the big thing in the world to worry about until you've done this other stuff. But at the same time, a virus is real and a threat, and you should understand that.
Greenberg points out this flu shot. We see a lot of bad virus type programs. You see the directly listed utilities. I really wonder how much of that is really virusing or just lousy programming. You know, when people start reading file location tables and doing stuff like that, bad code can do almost the same thing.
I mean, look, I get calls all the time. There are lots of things in this world besides viruses that are, you know, and lousy programs are certainly the vast majority. I get people that call me up and say, we run DBase on 50 systems, and we're having problems. We can't get data back some of the time. I think it might be a virus on my network. And you ask them questions, you know, is there some pattern? Like, does it only happen with very large databases? Gee, yeah. Gee, did you notice that DBase doesn't work for databases larger than this size, even though they don't advertise it? I didn't know that. Well, there you go. And of course, the problem is that, you know, they have their implied warranty of sale that they try to revoke. You know, we don't take any responsibility for selling you something that works. At the same time, we'll make sure you pay for it. At the same time, we'll copyright it, so we'll get all the full legal protection. Because the copyright laws are different now, we don't have to publish the source code, so we won't bring any advance about to society except to our pocketbooks. And this is the nature of the way things are right now, and it has to change. I mean, I tell PC user groups all the time, why do you run Lotus if they won't give you source code so you can check the integrity? Why do you run programs where they won't allow you to write protect your disk so you can protect it from these things? And the universal answer is, I didn't know there was any alternative. Then I say, how about these public domain programs, which you can have a little integrity bureau that checks these things out and puts them into your domain, and now you have 500 users and 10 people that spend some of their time checking the integrity of these programs you get in. And son of a gun, if we have 50 of these bureaus throughout the United States, you'll be able to take any piece of software you want, look at the source code, call up 50 different sites and have their integrity evaluation. And if they all say, I looked at the source code up and down, and it's clean and green and golden and wonderful, and here's the cryptographic checksums for it, and you check it against all the checksums, and you say, look, this is it. So that takes the user an extra 5 or 10 minutes, if you did it right. It takes every one of these people that work in the integrity bureaus an extra hour every week to ensure the integrity of the worldwide community. That seems to me like it's a good trade-off in that PC world. In your world, you have programmers that check on other programmers. You have change control, right? You look at when a program changes, you have somebody that looks over all the changes and says, yes, 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 what is this, right? You probably don't have change control on your executable code, and you probably should. So, okay, so you add change control in your executable code so that you check to make sure that executable only gets changed when the compiler compiles it, and that it only compiles once for every legitimate source change, and that it's examined first, and that all these procedures are followed, and you'll be a hell of a lot better off. No guarantees, but you can do that pretty easily and be a lot safer. You know, I mean, my job is to tell you what the ultimate reality is via mathematical demonstrations, then to tell you what the real reality is in terms of what you can do in practice, and hopefully to alleviate your fears if they're irrational, and to not alleviate them if they're not. More questions? Oh, I get to go home, yeah.
Let me ask kind of a bottom line question.
$347. Okay, next question now.
I understand everything that you said. It's possible for someone with a PC at home, using a word processor, take the finished document, which is a data file, take it to another computer somewhere, and say, load up that document, re-edit it, run it out. And that data file, that document may have
especially documents, yeah. Examples. Examples are always useful in demonstrating stuff. Profs. You all know profs? That's what Oliver North used. Profs. Profs used to have this minor thing in it. When you send a message, well, it still has some of it, but it doesn't have all of it. When you send a message on profs, and the receiver gets it, the first thing it does before it shows it to them is format it. So if you say this should be centered, it centers it. Okay, so when you look at the document you read, you don't get all these control codes, you get the document. So what happens in profs is there's this little command called .sy that you can put into a profs document that says, tell the system, issue a system command that follows, blah, blah, blah. So imagine you send, and it's been done, you send the profs document that says .sy, copy all the .sy lines out of this file into all your other profs documents. Okay? So now that has replicated itself. All those sy commands have replicated into all the other profs documents. And when you send a message out to anybody, it will replicate in all of theirs. And what you're going to find is if one of those .sy commands that got replicated was if the date's after January 1st, 1984, then delete all files, that this thing is going to spread like wildfire throughout the secure profs network, and on that date, everything's going to be gone. So the point here is that the document formatters are not limited functionality, they're general functionality. TROF and NROF, these Unix document formatters have this same capability. So do most of the IBM class machine document formatters. So do almost all of the high-class PC document formatters. Okay? So sending your document around is not an utterly safe way to do things. And by the way, those .sy commands can also decode a line of numbers and infect executable programs. And those executable programs can go off and infect other executables as well as other documents, et cetera, et cetera. So you can cross language barriers. And it's not hard to do, and we're not talking about 5,000 lines of code. I've written viruses that are 10 lines long that evolve. They evolve so much that there's almost no hope of you tracing the evolution. That is, there's almost nothing remaining of the original information. And what that is that remains has changed substantially so that you can't identify it. That will replicate itself in 2 or 3 different languages. Depending on how it evolves, it's harder to write one that has the maximal evolution and also all the languages and still get it into 10 lines. Runs in under a second and spreads like wildfire through a typical system. So that is the state of affairs. And that's right. You cannot trust documents any more than other programs because our document formatters have general functionality.
In 82, you wrote the first virus that ran for 84?
83. That's the claim. I mean, it's not my claim. I say it's the first virus because it's the first documented one.
If you hadn't and not assume someone else would, so I'm not putting the blame. But my question is, why did you write it?
I'm a researcher. I thought of this interesting idea that seemed to be a terrifying and unstoppable attack. And as a person that does research in computer security, I decided that it would be necessary to perform an experiment to establish the feasibility, to determine the attack times, and see what kind of infection times you got. That is to assess the threat. And once I saw how bad it was, I was planning to do my PhD thesis on defenses. Because at the time I said, this has got to be defensible. So what happened was in the next several months, I started to find out all sorts of negative results. And over the next several years, I found that there were some techniques you could use, that they weren't really that pleasing, but that they worked and they could be done effectively. And we did experiments on those defense techniques. It's about 2 weeks of writing viruses and 5 years of looking at defenses. And here's where we are now. We're at the point where we have some adequate defenses for many instances that are becoming available very soon. We have a world of people who have expertise and knowledge who want to find defenses, who are out there doing research and getting good results. And I figure most of my job is done because now we're going to have sound systems and sound defenses, and we're going to start protecting the integrity of information. But why I did it was to find out what the implications were.
You received
I'm still in the kitchen. Yeah, I got a lot of abuse. I'm still getting occasional abuse. Call the NSA. They won't tell you what they did, but we'll do it. I believe that where we came from was 20 years of trying to design systems to maintain secrets. Where we are is at the realization that integrity is more important in using computer systems and information systems than secrecy. And where we're going to go is we're going to spend the next 20 years developing systems that have a lot of integrity, and we're going to end up with a world which has high integrity systems that don't do dumb things, that don't have this stupidity of garbage in, garbage out. Instead, garbage in, you put the garbage in the trash basket and throw it away. Right? I mean, your typical typical user should not be able to type A into the input of a program and have it generate 47 errors and corrupt the global database. Okay? So I work a lot on maintaining integrity in systems, designing systems so that they look at themselves and at the inputs and they try to make sense out of things. And if things don't make sense, they don't blindly accept them. They say, this doesn't make sense. Why don't you give me something sensible? And I think that's where it will go. And that 20, 30, 40 years from now, all the systems out in the world will have a great deal of integrity. And you'll have high-speed, reliable communications, and it'll work very well. And it'll work just the right way. That is, people will spend the time to design, excuse me, to design the system and the interfaces so that it does just what it should do, so that it's easy to use and efficient and works correctly. And I think that will be the greatest progress in computing that we can ever make. Let's be careful about using those keywords that are. I don't like the word artificial intelligence because it's too commercial, and it has the so-called AI world has a history. In the 60s, they did great work in robotics and AI. They made essentially all the theoretical progress that's ever been made. And for the last 20 years, well, let's see, first we fell behind Japan for 10 years by doing nothing. Then we decided it's not acceptable for us to fall behind Japan by doing nothing. So instead of funding those few researchers that really have good advances in mind, we'll fund everybody we can find. And the way we'll decide who to fund is by what words they use this year. Like this year, it's neural nets. You can no longer get funding for expert systems. Well, that's waning. Neural nets is coming up. Let's see. When neural nets comes down, I think the next plan, well, let's see. They had artificial natural stupidity. I don't remember. They'll come up with another word in 2 years from now. So they're not AI systems. What they are is well-designed systems that are designed to maintain integrity, that consider the ramifications of input and state and determine whether that's going to produce an acceptable output in next state. In the language that I deal with in designing machines. As we start to think about it, we'll come up with new theories and new understandings, and hopefully we'll progress. I don't think the world is going to collapse tomorrow because somebody can write a virus today. And if you're afraid of that, have no fear. Like my uncle has a farm just east of Columbus, and if you want to grow food there, he'll let you come there and grow food, and you can still eat even if all the computers die. So don't be afraid. Charge ahead.
Did I understand correctly that you and Dr. Hopper are going to initiate research projects?
The relationship isn't that sealed yet. What the status is, I've been doing research in this for a long time, and I have a number of people that I deal with around the world. And to whatever extent I can, I interact with them to try to form a stronger research community. And it is my eventual intent, maybe sooner, maybe later, to build an environment for doing integrity research. An environment with support, hopefully in the university, that can do a solid bunch of work and make a lot of progress, and also promote teaching information protection and the education of the new breed of people that we're going to need to be able to deal with computer systems as they become a more and more vital part of our society. So, to whatever extent any researcher in the world is interested in becoming part of that, and anybody that has money is interested in helping to make that come about, I'm happy to get involved.
How does the federal government intelligently treat you? Give some indication, nothing.
Well, they have a somewhat different view of the whole situation. They perhaps don't agree that the best way to advance society is by getting a lot of people very knowledgeable and making rapid advances. They perhaps believe more along the lines of the way for them to get their job done is to restrict information about things that they can't do anything about. I don't know, one of the guys at the NSA, who was the director of the Computer Security Center, said to me that they will not fund any of my work, and they'll do anything they can to prevent anybody else from funding it. I explained that come hell or high water, the world's going to know the truth, and we're going to get systems with high integrity, and that if that steps on his thing, then his thing's going to get stepped on. Needless to say, he was not pleased with my attitude, and I was not pleased with it.
If I might just to comment on that, I might also mention that one of the differences, it seems that our areas are different, is that Bowling Green seems probably a different community. The people that we see and the users that we see do rely very heavily on PCs. I mean, most of the community that we see that is scared right now about viruses are the PC community. And they're the people that are out there screaming. I mean, there are auditing companies, big 8 auditing companies that go out armed with nothing but PCs that they do all their research on. And for them to lose a data disk, while admittedly a lot of people use mainframes for these big 8 firms, that is a real problem. And I've been approached by a number of people who are interested more on the PC side of it. And so there does seem to be a strong division in the area of research there. I'm not so much concerned with the mainframe viruses. I'm more concerned with the viruses that are running on the PC. And also, through the cooperation of a grant that our university just received, we're also interested more in, I guess you could say, who is going to be attacked by these things. In other words, when are you going to see widespread virus attacks? When are you going to see planned virus attacks in a PC setting? And so there's a little bit difference in the two kind of research that we're doing.
Right, so they receive funding for that.
No, you want to bet? Yeah, my paycheck.
Well, what about the PC network that may be infected from being networked through a mainframe network?
I'm concerned with the whole problem, to the extent that I think that the present financial risk lies mainly in the mainframe. I will tell you that when you do your risk assessment, that's what you should consider. When the situation changes, as perhaps it is slowly changing, then that will be how your assessment should change. I should point out that PCs of the form where you don't have a safe operating system, where you don't have any protection at all, you have a machine where anybody can execute any instruction, are on their way out. And 10, 15 years from now, every PC, like every mainframe now, will have an adequately protected operating system and that level of integrity. And when that all happens, we'll still have the issue of how do we protect integrity, and hopefully the results that I come up with that apply primarily to mainframes today and networks today will apply to those systems even more than they apply to PCs as they exist today.
One other question, sorry about that. But I assume you're talking about something that's Mac-like, user-friendly, or parsec-like, I guess, with Xerox. You're saying the scores virus, and I don't know the Mac very well, but the Mac doesn't give you a problem, does it? How does the scores virus affect you in this high-power-based user?
See, this is why I always start at theory. It's very important to start at theory because that's what gives you deep understandings. See, without knowing any of the details of how the Macintosh user interface works and to what extent you can get through the user interface, I know you can write programs. I know that you can share information. Therefore, I know that viruses are possible. I know that the operating system doesn't have any explicit protection from the rest of the world. Hence, I know that the operating system can be attacked very easily as well. So I always begin at the theory. And now you ask me, on a Macintosh, what is the specific mechanism for compiling a program to do this, to insert into that, to do that? I'll say, well, I'd have to really study that if that was the important thing today.
No, I guess what I'm driving at is it seems like we're going to that kind of interface where users are not encouraged to use the command line. It seems like on personal computers, a command line is always going to be available in some way, much with the Mac is. You know, when you
That's not right. No, that's not right. When you say available, I can take those programs on the Macintosh or on the PC, and I can make relatively minor modifications to where when you put that disk in and you boot that computer up, that's where you are. You have limited functionality. You can use menus, and they can have pop-up menus, and you can create new and better pop-up menus to do new and better things, but you don't have general-purpose functionality. Limited set of programs, limited set of things they do. They do your spreadsheets, they do your databases, they do your integrated documents, they print out beautiful integrated documents, but I don't have something in my document formatter that lets me say, do this general purpose thing. You know, and we can do that. And we can make a very effective, very safe environment for that if we, of course, can protect the people that generate that software, which, you know, today is where one of the major holes is. But that's a very viable alternative for most things that most people do. And that's right. Most users of computers 20 years from now will not know anything about programming any more than most users of computers today know anything about programming.
My only comment on that, I agree with what you're saying, is that I don't know the Mac either, but I'm assuming that the store is operating on the same basic principle. You know, you put in the old diskette and there is an operating system for internal I/O, not for you, the user. And you've got this integrity problem. You've got this program that's on there that does the corruption of your system.
I don't think it's particularly directed at the system. I think, you know, it goes into the Finder, but that's just a regular user program, and it goes into various other programs, but they're just regular user programs. I don't think it exploits any operating system features. That's right. That's right. Oh, hey, integrity is a problem, and we have to address it. I agree. Command lines are not the ultimate solution.